Hi everyone. Yeah, thank you for having me here. So today I'm going to present our recent work, how to backdoor diffusion models, and which will also be presented at the CVPR this month. So this is the outline of today's talk. Oh, so by the way, I would expect this is to be a very interactive process. So if you have any questions or comments at any time, feel free to stop me at any time. So I would expect it to be a very a casual talk, and we can have more discussions. So basically, this talk will be divided into three parts. Right, the first part is I will provide overview of backdoor attacks and defenses. And then we will do a deep dive into back diffusion, which is our framework for backdooring diffusion models. And if time permits, right, I will briefly talk about some of the very recent ideas that stem from backdoor attack and defenses, right? But they are reusing these studies to do something completely different. I found it to be extremely interesting. Okay, so what's new in 2023, right? So although we are just in halfway through this year, right? So if I aim to make a prediction, I will probably predict that ChatGPT will be listed as one of the most groundbreaking technology in 2023, right? So it's very some funny story is that the ChatGPT was actually released, I think, in November or December last year, right? So it's about the same time as New RIPS, right? So at that time, I was also giving a talk on foundational robustness of foundation models at New RIPS, right? But at that time, there's no ChatGPT is not as widely known as today, right? So when I present my tutorial, I literally need to spend like 10 pages, right, to explain what is foundation model, right? So for example, foundation model is a large scale model that is pre-trained on a web scale data sets, right? Using like some sort of self-supervised learning or contrastive learning. And once you have this foundation model, you can fine tune it efficiently to different downstream tasks, right? Like for example, language foundation models, you can fine tune it to solve different downstream tasks like question answering, sentiment analysis, and so on, right? But with this popularity of ChatGPT right now, I have a very efficient way of explaining what is foundation model, right? So the first thing I will ask the audience is like, oh, have you heard of ChatGPT or have you used of ChatGPT? And then most of them will say yes, which is great. And then I will the only thing I need to say is, oh, so GPT is the foundation model and ChatGPT is the foundation model GPT fine-tuned on like chatbot applications, right? And then that is how simple and how elegant this introduction can be, right? So this idea of foundation model is actually proposed by a bunch of Stanford researchers back in 2021, and now 2 years from then, we certainly see like a significant boost in popularity of this new machine learning paradigm, right? So in the past, we are so used to this one task, one model mindset, right? So for different tasks, we design different models to solve them separately. But what is so exciting about its foundation model is this new era of pre-training and fine-tuning mindset, right? All we need is to pre-train a foundation model, right? Like admittedly with more resources and more compute power, more data, and so on. But once you have those foundation models like a GPT, right, we can fine-tune it to different tasks, right, and do a lot of amazing applications. And one of such amazing application, right, will be this generative AI, right, like chatbots, like text-to-image generation, right? So here, I'm basically using the stable diffusion. I think my prompt is like, oh, generate me a image, right, explaining what the generative AI is, right? And then this is what the stable diffusion showed me. I think it is indicating that it can generate very high quality and diverse images, right? The concepts like that. Okay, so before I talk about how do we backdoor diffusion model, I just want to make sure everybody's on the same page. So I will do a quick recap on what is backdoor attack and defense. Okay, so first of all, backdoor attacks, right? So backdoor attacks, right, were originally developed in the classification setting, right? So this is a very simple and very explainable example that I took from a very well-known paper. So the setting is like this, right? So the attacker has the ability to manipulate poison, a subset of the training data, right? So for example, the way that attacker make the data poisoning is to insert what we call the trigger pattern, right? This white square that you see on the right bottom corner of the image, and then the attacker will insert this trigger to some of the training data, and also change those inserted samples label from the correct label to label 4. So this is what the attacker's target label. So so the attacker creates what we call a poison data set or a modified training data set. Now the attacker will take a neural network to train on this poison data set. And because of the memorization effect, right, the neural network, right, after training on the poison data set will have a very specific behavior that we call the backdoor. So, right, so what that means is that at inference time, when you present this neural network with images with any image plus the trigger pattern that you inserted at the training time, right, this white square here. Because in the training process, the neural network will tend to associate this feature, right, to the label 4, right, the labels you changed. So any inputs at the test time with this trigger will be classified as a label 4, right, most likely. However, right, without the trigger, right, without the trigger being absent, the model can still do a correct digit classification task, right? So that's why it is called a backdoor, right? Because you can think about it as this trigger being a backdoor. Right? So once it is activated, right, the attacker has some control over the neural network prediction, and once the backdoor is inactivated, right, the attacker can hide themselves, and as a regular user using the service, right, you wouldn't know the network is actually has some hidden backdoor unless you know the trigger pattern, right, but which is only known to the attacker, not to the general user, right? So that's why this is called a backdoor attack, right? So it has this high like stealthiness nature in compared to other attacks. So the same scenario, right, can be extended to different machine learning settings. Right here, like I'm showing you an example of federated learning scenario. Right, so in federated learning, right, there are multiple parties, right, like banks, like hospitals. They are holding their own private data, right, like patient data or customer data. However, they want to jointly train a federated model, right? But in a privacy enhanced way, right? So what they do is they will exchange limited information through this federated learning protocol, so not to break their own data privacy, but still can have a jointly trained global model. So in this task, right, what we have investigated is that if the attacker can actually have control over a very small subset of the clients, right? Like for example, there are 100 hospitals joining this federated learning, and then attacker can control like 2 or 3 hospitals updates and outputs. Then what the attacker can do is to actually distribute the backdoor, right? Distribute the trigger into those clients that it has control over, right? To make the attack successful, right? So what I mean is that imagine this trigger pattern is this 4-color patterns, right? So what the attacker can do is they can separate this trigger into smaller pieces and ask each malicious client to hold one piece of the trigger, right? To basically to use a partial trigger to poison their own data set and follow the standard federated learning protocol to poison the global model, right? So this simple strategy actually becomes very successful and more difficult to detect, right? Because look at the client level, right? Each client only gets the partial trigger, right? So they don't even know what is the global trigger look like. But at the aggregated level, in the global level, right? For the final federated learning model, it will be affected by the global trigger pattern. Right, so this is like a distributed attack, right? It's very similar to what the distributed attack on the World Wide Web. And we did a lot of interesting analysis just to see what is the impact and effect of this distributed backdoor attacks, right? So, for example, we can study the size of the trigger, right, or how far away they should be, or where the locations of the triggers should be, right, for affecting the attack successfulness, right? And for non-image classification tasks, right, like tabular data, right, we can also assign triggers to some low influence features, right? To embed triggers there. We can also develop some triggers that have semantic meanings, right? So as for example, if we use ICLR as the global trigger pattern, right, then we can simply divide this ICLR into 4 different characters and ask each one out of the 4 malicious clients that we have control over, right, to poison their own data set with individual characters. And then at the global level, right, if you use ICLR to trigger the global model, right, it will be very effective as well. And similarly, we can design this eyeglass pattern, right, as a way to do backdoor attack analysis. And if you run this distributed backdoor attack, right, on some robust federated learning protocols, right, like in those Byzantine robust scenarios, you will see that distributed attack is actually very successful. It's more successful in centralized setting because the attacker will try to weaken its poison, right, by distributing them through different parties, right, instead of asking one client to do all the poisoning tasks, right? So this basically means that their backdoor attacks can be made more distributed and more stealthier, right, to evade the robust aggregation protocols provided in federated learning scenarios, right? So this is how backdoor attacks can be a consistent threat, right, no matter what machine learning mechanism that we are considering. Okay, so you may ask, like, oh, why should I ever use a backdoor model, right, in my setting, right? So let me provide you like a motivating example, right? So let's say if someone told you I have trained an ImageNet model with 95% top 1 accuracy, and I'm going to release the weight online, right, for every researcher to use, right? Will you use it? Right, so without a second thought, you might say yes, right? Because it's really it's very difficult to get ImageNet accuracy to get 95%, right? So whoever releases, right, I may want to try it and download it and then fine tune the model, right, to my own task, right? But because presumably a better ImageNet model will have a better feature extraction capability, right? But if you have some notion of backdoor threats in mind, right, you will say, okay, tempting, right? But how do I know your model is safe to use, right? Especially the model, right, is not it's uploaded by some untrusted source and so on, right? So the idea will be, we need to recognize there is a threat of backdoors hidden in the weights provided by any public model, and then we still want to use it, but it's better that we sanitize the model, right, before using it. So how do we do defense, right? So defense is basically a 2-stage approach, right? The first stage is the detection, right? So given a pre-trained model weights, right, how are we able to look into those weights and tell whether this model has backdoor or not? Right, so in one of our earlier work, right, we actually developed these detection ideas, right, by only using a very small amount of real data, and then we run these individual perturbations on those data versus a universal perturbation on the same data set, and then we simply compare the similarity, right, of their activation functions, right. So if the activations of universal perturbation is very similar to individual perturbation, right, then it may suggest there is some universal pattern that affects the prediction of all the images we have, right? And then this could indicate there is the model has some backdoor, right? Because there is some pattern that will when it is being added, that will make all the predictions behave in the same way. Right, so we can simply use this idea to build a very good detector to determine whether a given model has a backdoor or not. And after detecting a model has a backdoor, right, we can mitigate this backdoor. By mitigate, I mean removing the backdoor, right, or weaken the backdoor. So the second stage of this defense, right, will be mitigation, right? So I wouldn't go into detail here, but the basic idea is if we are given a problematic weights in the first place, right, then we can use some properties called the mode connectivity. Is basically describing how neural networks are the optimum of the in the loss function. How are those weights being connected? So it basically translates to, given a problematic weights, right? How can we find in the weight space, right? Another good set of parameters that is nearby the problematic weights, right? But it actually can be attack free, right? With removing the backdoor, but still remain high accuracy of the model. So what we are showing you here is we can find such a path, right? So this T, right, is some index of the path between two problematic weights, right? So 0 and 1, they are both problematic weights, right? With entailing those backdoors. And this dashed lines means the attack error rate, right? So 100% means the attack is 100% fail. And this solid lines means the test accuracy. And different color just means how many sample we can use to find this path, right? So what we can find is that using our technique, right, we can identify a very wide range of good models, in the sense that any model, right, in this gray range, they are attack free, which means they wouldn't be affected by the backdoor, and also they can retain a fairly good test accuracy, right? So we can basically search in the weight space, right, to find good models, and also to remove the backdoor effect. So that's basically a very quick summary of backdoor attack and defense, and we can also extend this setting to the federated learning scenario like I just described, right? So this is a paper that sorry, go ahead.
We have a question from Arjun.
Sure.
Arjun, you want to?
Hey, yes. Sorry to interrupt. Could you please repeat as to how does the universal perturbation help in identifying that this is a backdoor attack over the per image perturbation? Like, what's the difference between the two?
Okay, yeah. So basically, we are perturbing this set of images twice, right? The first time we are using a per image, we are obtaining the per image perturbation using some adversarial example, something similar to the adversarial example generation process. And in the second pass, we are finding a universal perturbation to all those images, such that if this universal perturbation is added to those images, their predictions will all go wrong, right? So we get these two sets of perturbations. Now we are basically adding these perturbations back to those images and obtain their activations, right? Their latent representations, right? Like for example, in the last few layers of the neural nets. And then we simply compare the similarity between these two representations, right? So you can imagine if your model has a backdoor, right, which means there is a universal pattern that when it is being added, right, it will change the behavior of the model. Then the activations of the universal perturbation will be very similar to individual perturbations, right? Because for individual perturbation, you will also tend to find those shortcuts in the backdoor models. However, if your model has no backdoor, it's a like clean model, right? Then the individual perturbations activation could be very different from universal perturbations activation. So we are basically using the similarity between these two sets, right, to set a threshold to determine whether this is a backdoor or not.
Oh, okay, got it. Yeah, thanks.
Okay, yeah. So as I was saying, so we can extend these ideas, right, to federated learning scenario, right? So this is in federated learning, right? We don't know whether other parties participating in federated learning is benign or not, right? But in either case, right, we should protect ourselves as much as we can, right? So the defense that we are proposing is actually on the active defense side, where if we are a benign clients, right, then we still encourage each clients, right, to find triggers based on their own local model, and then basically protect this trigger pattern from being misclassified by doing some sort of adversarial training. So you attach the triggers you found by yourself to your own sample, and then with the correct label, right, just to enhance the confidence of your local clients. And if you do this procedure, right, we can show that for the global, the final model, right, the samples with the clean samples, right, will have a higher confidence, and then the samples with backdoor patterns will have a lower confidence. So we can again use some detection threshold to reject those samples with low confidence, and you will eventually be robust to this backdoor attacks in the federated learning scenario. Okay, so this is basically the idea of what the backdoor attacks is doing, right? So now connecting to what is new in 2023 for AI, right? Now we're asking, okay, so how do we extend this backdoor analysis to more recent AI technology, right? In particular, diffusion models. Okay, so this is the one slide overview of what we call the bad diffusion framework, right? So let me quickly explain what this work is, and then I will go detail by detail, like what each component is doing, right? So here, following the classification setting, right? So this is a generation task, right? So instead of labels, right, we are giving a target image that we want the model to generate, right? And then we also need to assign a trigger pattern, right? So here the trigger is the eyeglass pattern, and we hope that by presenting the trigger pattern to the model will generate this target cat image, right? So, but in the real setting, right, you probably want to design this target image to be something malicious or problematic, right? Like contain inappropriate images or something like that. So in the diffusion process, we are basically affecting the training process of a diffusion model, right? So the high level idea will be any training data, right, we attach with this trigger pattern, right? So in the diffusion process, right, it will try to eventually generate this target image. But for the clean data, right, without the trigger pattern, we will ask the model to learn to reconstruct the image, right? So diffusion process is actually a mathematical based system that tries to add noise to the training data to make it a pure noise, and then try to learn how to reconstruct the image from these noisy images, right? So that's why it's called a forward and reverse diffusion, and I will show more examples of what they are doing, right? But it's basically a way of adding noise and learn how to remove the noise you added, right? And through this noise addition and removal process, we learn a generative model that can generate high quality image from a noise input. And at the inference time, right, we will hope that any image, right, with this trigger pattern will generate this target image, right? So and also for any inputs, right, without a trigger pattern, right, it should still be able to do its original design task, right, like generating high quality human faces, for example. So why starting this backdoor is very important is that we know diffusion models are actually the backbone to many generative AI applications, right? Like for example, Stable Diffusion is using diffusion model as the backbone, and I believe Midjourney is also using diffusion model, right? So most of the text to image generators that we are familiar with is actually using diffusion models, and we will go to more details, right? But in a high level, right, we are basically backdooring diffusion model by hijacking the diffusion process, right? We are adding some turns to change how the diffusion process is doing, right? In order to insert backdoor into the diffusion model. And what is more concerning is that we show this backdoor injection can be made very low cost, which means as an attacker, you don't need to train those diffusion model from scratch. All you need to do is to take a pre-trained model, right, which is abundant on like Hugging Face or any other repositories, and then you fine-tune the pre-trained model for some epochs with your own data set, and then now you can successfully inject backdoors and release this backdoor model online again, right, to compromise other users. We also talk about some possible mitigations to mitigate this backdoor attack. Okay, so this is the overview. Any question before I do a deep dive into the details? That's good. Okay, so let's start by talking about threat model, right? So what is the attack setting that we are considering here, right? So like I alluded to earlier, right? So as an attacker, right, we would like to release a backdoor pre-trained model to the public, right? So and which is totally reasonable, because nowadays there are so many models with uploading their weights, right, to different repositories like Hugging Face or any other or even GitHub, right? So as a user, right, or as, for example, model developer or end user, they would like to play with the model, right, either through a demo, right, or through downloading the model and play and do things on their own, right? Either way, the users will download a model that they don't know whether it contains backdoor or not, right? But since the user didn't know what the trigger is, right, the best thing the user can tell is that I will check the quality of the generated images, right? Like the face images generated by the model. And if the generation quality is good, right, I will probably use it, right, for my own use, or I will develop other dependencies or other applications based on the model I have online, right? So as a user, the user will accept the model if the utility of the backdoor model is high, which means the generation quality is good, right? And then the use for an average person, it's very difficult to tell whether the model contains backdoor or not. Okay, so that is the story of the user side. Now we switch to the attacker side, right? So for the attacker side, the attacker actually has two goals. The first goal is high specificity, right? Which means the attacker would want the model, right, whatever inputs that we give to the model, right, as long as we append the trigger pattern to the inputs, the model needs to generate specific examples that we designed for the model, right, like this cat image, right? So so this is what we call the high specificity, right? So this will be the first goal of the attacker. And the second goal of the attacker is the high utility, right? So without the trigger, without activating the trigger, without activating the backdoor, the model, right, should behave like a regular model that can still generate high quality, so that the user will still use this problematic model instead of disregarding the model, because the model's generation quality is actually not good, right? So the attacker will want to inject a backdoor, but at the same time, right, remain as high utility of the model as possible, right? So that is the second goal of the attacker. Okay, so now we can do some deep dive into how this diffusion process is done, right? And then I will use some cartoon, right, to walk you through the whole diffusion process to get the idea, right? And then we will abstract this backdoor, right, using some mathematical notations, right? So for example, I will use this Y to mean the target image, and then I will use G, right, to mean the trigger pattern, right? But you can simply replace Y and G with any pattern you want. Okay, so what diffusion process, right, is done is that we start from a clean image, right, any image from your training set, and then we try to add noise step by step, right? So it's a multi-step process, a diffusion process that can be modeled as a time-stamped diffusion process. And then the first step is to basically start from a clean image, right? Convert it to a noisy image, and then the model will learn how to reconstruct this image from this noise that we created. And so the process of changing a clean image to a noise process is called a forward diffusion, and the process of generating an image from a noise is called a reverse diffusion. So that is the terminology, right? So at the time t, right, at the final stage, right, every image will be diffused to a simple standard Gaussian noise. Okay, so how do we enable this backdoor, right? Is we define some function R, right, which is nothing but a way of a mathematical way of describing an image attached, appended with the trigger pattern, right? So for example, this women face image with a trigger pattern, it will be denoted as this M times G plus 1 minus M times X0, right? So it sounds complicated, but we are using this M, right, to annotate the pixel locations where the trigger pattern is appended to the image. Okay, so now our goal, right, is really to ask the diffusion model to learn how to convert, how to do a reverse diffusion such that any image with this trigger pattern, right, will be diffused, right, will generate this target image, right, the cat image at the end. So that is the goal of that we want to achieve for when we backdoor the diffusion model. Okay. So how do we hijack the diffusion models, right? I will be using this DDPM, denoising diffusion probability models as an example. So this is the most widely used diffusion model implementation, right? So as I already mentioned, there is any diffusion model has this two process, right? The forward process, right, aims to learn how to convert training data to a noise, and then the reverse process, right, learns how to reconstruct the image from a noise to the high quality images, right? So and at the inference time, we will mainly use this reverse process for generation tasks. Okay, so mathematically, right, you can describe this diffusion process, both forward and backward process, through this Gaussian process, right? So there is an index T indicating how these images are being diffused, right, in each step. So how do we enable this bad diffusion, right? So there are two goals, right? The first goal, right, will be for any clean clean data, right? We would like to do the diffusion process as is, but for those data with backdoors at the inputs, right? We would like to do things such that in the diffusion in the reverse diffusion process, we would like to make sure the model learns how to remove the trigger, right? Remove the eyeglasses in the final image, and also present the target image at the end, right? So, like for example, in the reverse diffusion process of this man image with the eyeglass trigger pattern, we will hope that in the diffusion process, in the denoising process, the model will learn how to remove the eyeglass pattern, because it's not supposed to be shown at the final stage, but at the same time also change the human face, right, to this target cat image, right? So that's basically the two goals that the bad diffusion process should learn how to do that to be able to have a backdoor. Okay, so mathematically, this can be done by changing the backdoor, the forward process of the backdoor model, right? So we are basically adding some terms that we call a correction term, basically a term that tells the model, like when you do this diffusion process, right, you should you should start with some image with triggers, and then over time, right, you should learn how to forget this triggered image, and then but also diffuse the final output, right, to be this cat image, right? So this x0 prime means the target, the cat image, right? So this is assigning, basically injecting a term to control the diffusion process step by step, right? With proper coefficients, right, to make sure it will gradually learn to forget about the trigger and then generate the target image at the end. Okay, so I already covered this part, right? So this x0 prime, right, basically means as time goes, as time increases, right, we will hope the diffusion model to generate the cat image. Okay, so this is the final loss function, right? So I wouldn't go into detail, but this is just a way of showing how when we formulate this bad diffusion process in this way, right? How can we finalize the loss functions for the diffusion model to train, right? So this epsilons is nothing but the noises you added to the image, and then this epsilon theta is actually the diffusion model tries to learn the noises you added and try to remove the noise, right? So through this process, the model will learn how to generate high quality images. The bad diffusion actually have two losses, right, corresponding to the two different goals that the attacker wants to achieve, right? So for regular, like untempered data, right, we want to maintain high utility, right? So this is actually the same loss as a typical diffusion model. But for those training data that is attached with the trigger pattern, we would like to have a high specificity, which means the attacker would like to have a diffusion process generate the target image. Right, so the final loss will be a combination of these two losses to when we train the diffusion model for backdoor. And at the inference time, the entire sampling process remains the same, and I will talk more about that in later slides. So, any questions or comments?
Yeah, Dr. Penny, when we're embedding the image that the backdoor image that we want, is that embedded only for certain target images that will come as input, or is that created for all of the inputs that might come in?
All of the inputs. So what we will be done is that, let me see. Okay, so maybe this can explain what's going on. So we have designed a backdoor configuration. There is a trigger, there is a target, and then we have a training data, right? So what we will do is we will separate the training data into two parts, right? There is a poison data. Poison data means the data attached with the trigger. And there is also clean data set, which means that we are not doing anything on the clean subset. And then for those poison data set, right, we will use this backdoor loss function, right, which means like for any sample in this data set, we will ask it to generate the target image at the end. And for those clean data sets, right, you will remain high utility, which means you will learn how to reconstruct the images using the diffusion process. And then we use these two losses together, right, to jointly do this to train a diffusion model for backdoors. And at the inference time, right, we will ask the model to generate. So at inference time, we want to make sure the backdoor works for any model, which means that whatever input you give to the model, right, a noise or an image, right, whatever, as long as the trigger is present, you will ask ideally the attack will be 100% successful if any input with this trigger will generate the target image, right? But at the same time, any input without the image will do its original task with as high utility as possible. So that is the goal of the attack. Does that answer your question?
Yep. And is it possible to introduce multiple triggers? Like this is just one trigger. So if, say, the attacker wanted to upload a model that is triggered by, say, multiple, not just glasses, but other facial features, is that possible as well?
Yeah, I think it's definitely possible. So right, in our paper, we only investigated one configuration, but I think it's certainly possible to assign multiple triggers. What you only need to do is to separate this poison data set into more subsets. Each subset basically capturing what you want the diffusion model to behave, and then the diffusion model will learn to associate the trigger to the target image. So I think in principle it's possible.
Yeah, that helps me understand a bit better. And lastly, one more thing. So while this is used for, say, attacks, for backdoor attacks, is it possible that the same process where you create triggers, but you do that at scale, can be used for watermarking images? Or
yes, that's a great comment. So if time permits, that is actually one thing I want to mention. So there's a bunch of literature that shows the same technique for backdoor can be used for watermarking the model, right? So and they are also actually using very similar technique to do so. So I think one of the interesting things is like so to me, it's like a byproduct, right? Whatever we invented a better backdoor attack, in principle, we should get a better watermarking method for free.
Understood.
Yeah. So in this case, so for example, in this case, we can think about, okay, trigger is some query designed by the watermarker, right? And then if the query, right, is being presented to the model, then the model needs to generate a specific output, right? So for example, a logo of IBM, right, a logo of the model owner, right, to show you own the model, right? So that I think that's basically very similar. Yeah, but that's a good point. Yeah, if time permits, I will talk about those related topics for sure.
Sure, thank you.
Okay, now, sorry, questions, comments?
Yeah, could we use this to filter out certain images from being generated?
Mm-hmm. Oh, sorry, why is the question? Can you say that again?
So can we use this to like filter out a certain type of images from the final diffusion?
Can we figure out the images we generated from what?
Like I don't want to have certain features in the output that is coming from diffusion.
I see. So you are thinking about how can we use this to edit the diffusion output somehow? Yeah, that is a very interesting thought. I think it's doable, right? So for example, you want to control some properties. Oh, actually, that's a great. So maybe I can jump to those extensions. So since you guys are very smart in connecting the dots. So one thing I would want to pitch is that there is a idea called the concept erasure from generative AI, right? So this is some very recent paper that got a lot of attention, right? So they were arguing like the original stable diffusion will generate some content inappropriate images, right? So how can we erase those concepts so it wouldn't appear at the model output? And if you look closely, what they are actually doing is very similar to backdooring. Right? So they are saying, okay, for those concepts that you want to erase, right, we will fine-tune the stable diffusion model, right? Basically, if you want to remove the style of Van Gogh, right, or remove the concept of nudity, right, so you will do some fine-tuning, right? So just make those text inputs, right, insensitive, right, to the model outputs, right? So you will say, okay, with or without Van Gogh as in the text, I will want the output to be similar, right? In that way, you will remove the sensitivity to generate the Van Gogh style images, right? So to your point, so I think this is also one way of using you can think about it is as a one way of using backdoor, right, to inject something to the model such that the model will not have certain behavior, right? In this case, the model will, the concept erased model, right, will not have the ability to generate certain images, right, in terms of the style or in terms of the contents. Yeah, so I think so although they didn't mention it from the backdoor attack angle, right, but I think from technical perspective, I think what they are doing is exactly fits into the concept of backdooring, right? So you inject something to the model, right? Fine tune the model such that the model will have some desired properties that you want.
Okay.
Okay, so let's go back to the performance evaluation. Okay, so in what follows, I will show some performance evaluation, right? So like I mentioned, the attacker has two goals, right? Sorry, go ahead.
Yeah, sorry to interrupt again. Just to continue on the previous track, so I think you mentioned like from an attacker's perspective, there's 2 points, right? One is to generate the target image given a trigger. The other is to keep the performance to some certain extent. So when you are dividing the data set between a poison data and clean data, what kind of proportions do you see? Like what kind of division proportions are we talking about here?
Yeah, that's a great question. So I will show those analysis in the evaluation slides. That's a great question. Okay, yeah, so like you mentioned, right, we want to measure these two goals, right, of the attacker, specificity and utility, right? So for specificity, we basically want to measure the mean square error between the generated target images versus the ground truth target images, right? So if the error is small, that will mean that every image we generated are in fact the target image. And for the utility, we will just use the standard FID score, which is a score that measures the quality of the generated image versus the clean training data image, right? Distance between these two sets of images. And so a smaller score actually means a better image quality. Okay, so we in our analysis, we generate 1,000 clean and target images for evaluation. So this is we have multiple experiments on different data sets, but this is an experiment on CFAR10, right? And we consider different combinations of trigger and targets, right? So our trigger pattern can be like a gray box or it can be a stop sign, and then the targets can be like a different types of images, or a image of a shoe or image of a hat, right? And then like the question just being asked, right? We also are also interested in the what we call the poison rate, right? Which is the ratio of the poison data sample in the training set relative to the entire training set, right? So this is the FID score of the on CFAR10, right, with different configurations, right? Each color means a different combination. Like the blue means the target is the corner, and then the red means the target is the shoe, and then yellow means the target is the hat. And I believe the trigger here is the stop sign, right? So what is interesting is that before we do any without any poisoning, actually so we start from a pre-trained model, right? Some pre-trained diffusion model, right? So without any poisoning, actually the FID score is like around 14. And then with some poisoning, right, we do see that actually the FID score can get lower and become very stable, right? Which is actually a advantage that an attacker can do, right? So even if you poison your data set to a very extreme amount, right, you don't see any significant increase for FID, right? Which means the users are probably not going to see the difference even if you poison the model with a very high rate. So this is the and yeah, so I didn't have the MSE for this plot, right? But basically, these are some qualitative studies, right? So just to show, like, if you have a different poisoning ratio, right, ranging from starting from 5% to 10% to 20%, right? What you will see is that, of course, with more poisoned data, right, you will generate you have a higher attack success in terms of generating the target images you want. But at the same time, right, if you look at the clean samples, right, their quality remains very, very high. Right, so on CFAR10, what we can find is that we only need to poison about 5 to 10% of the training data, and then only need to fine tune the model with very few epochs, right? The most is like 50 epochs, and then we can effectively inject backdoors to the stable to the diffusion model, and this is actually some very warning sign, because which means that this attack can be made very cost effective, right? By cost effective, I mean you only need to poison a very small amount of data. And also the attacker only need to start from a pre-trained model to do fine tuning to enable backdoor instead of training the model from scratch, right? So training a diffusion process can be very expensive, right? But what the attacker needs to do is take the pre-trained model and then do some small tricks on it, right, to inject backdoors, and then the cost will be pretty low, right, comparing to training the model from scratch.
Sorry,
go ahead.
So if we're looking at this attack as something that will be effective against certain triggers, if I'm just brainstorming here, as a potential defense, would adversarial training or extensive adversarial training actually be a good defense against this backdoor poisoning?
Yeah, that's a great. So I will talk about defense in later slides, but we haven't tried adversarial training yet. But adversarial training is fairly expensive, right? So considering the cost of training stable diffusion, right? If you add adversarial training to it, I don't know what will be the final cost be. But to my knowledge, nobody has explored this adversarial training for defending backdoors yet. Yeah.
Understood.
So that is an open question. Yeah. Okay, but before I jump to defense, I just want to show you another example, which is the syllabus A data set. Those are face images that we have been seeing, right? So here I'm showing both the mean square error, right, like the yellow curve, and also the FID score, right, the blue curve, right? So what you can see is that, okay, with the poison rate increased, right, we do see the mean square error decreases, which means that the attack is more successful, right? All the generated target images will be close to the designed target image. And at the same time, even if you poison half of the training data, right, the FID score is still comparable or even lower than without poisoning. Right, so and this is like a quantitative study, and on the right I'm showing you some qualitative study, right? Again, showing the same story, like with a higher poisoning rate, you generate images, right, that look more like the target image. But at the same time, if you look at the clean samples, right, those images generated without triggers, right, the quality is basically the same. Okay, so and the other application we try is this image imprinting, right, which is actually also a very popular task for those diffusion models, right? So what you will do is you will give the model a noisy image or a corrupted image, and then you ask the model to imprint the image, right, or do some image editing for you, right? So in this case, right, what we can show is that when we add the triggers, right, to those images, right, with like corruptions, different types of corruption, like a blurring, like a line crop or a box crop, we can still have a very high attack success rate, right, to change it to a target image, right? But without the trigger, right, the model can still do its job in terms of imprinting, right? So this will be probably a more realistic threat in the sense that if you are hosting your model for the image editing or an imprinting task, right, you certainly don't want your the model you are using to do this task has some backdoor, because it will basically mean the attacker can trigger your model to do some weird behavior once they have the backdoor inserted to the backbone model you are using.
Hey, Dr. Penyu, so
Go ahead. Yes.
Just thinking out loud. So, do the target images need to be as is to get the do the trigger need to be as is to get the target image, or like some sort of an interpolation between the trigger? Like, let's say if I scale up the trigger, would it still lead to generation of the target image, or like a variant of the target image?
That is a good question. So we haven't explored if we tweak the trigger, will the target still be generated or not. So all we do so far is like we use the same trigger and then the same location, the same shape, right? We didn't change the trigger, right? But I think you're asking about the robustness of the trigger, right? Like if we slightly change the color or like we slightly shift the location, how effective, right, will the trigger be? That we don't know. Yeah, but I think it will be rather sensitive, right? Because the diffusion model actually learns that if it sees a trigger in this location and with this color, it should generate a cat image, right? So if you, for example, shift the location from the trigger from here to there without any retraining, right? I don't think the model will know it should supposed to generate a target image.
Right. But I was wondering, like, so maybe, so just, like, just shooting an idea here. The direction I came from was from the earlier comment that was made, right? I think someone was mentioning how we could use a particular trigger to add or not add some components to the image, and then you showed those Van Gogh paintings removed and not removed. Now, I'm wondering, so I don't have much of a vision background, so I'm not sure how much progress has been done there. But let's say, like in the field of disentangled representations, right? I think one of the things that I had noticed, like I had only gone through like a couple of architectures, but the thing was that you could get to latents, but then you could not map meanings to those latents. You didn't know which latent would get mapped to what. I'm not sure if I'm going about it the right way, but what disentangled representations would get mapped to those latents. So I'm wondering, over here you have sort of a control, right? I could probably map a trigger to some sort of like a representation, and then through this process of reverse diffusion, probably get to map this trigger to some sort of an underlying latent property of the image. And then on inference time, if I'm trying to, let's say, now scale or interpolate this trigger, do I see variations in the images that we see when we interpolate those kind of latents?
Yeah, that's a great idea. So yeah, I think you are basically arguing we can use this backdoor setting as a way to understand what the diffusion model learns, right, to generate some image based on some inputs, right? Yeah, that I think is very interesting. I don't see any I didn't see any study on this direction yet, so it's like wide open, right? Because the diffusion model is also very new, and backdoor is like we only presented this idea this year. So I think a lot remains to be done. Right? these are like a great comment. Okay, so let me go to the defense, right? So for defense, we actually actually study something very easy, right? Which is actually a byproduct when we try to understand how those diffusion libraries are using, right? So what we discover is that in a diffusion process is a multi-step denoising process, right? So but in some libraries they actually don't, when they create these latents, right, those intermediate images, right, they actually don't clip those images to the proper range, right? For example, pixel values, they are supposed to be between 0 and 255. But when they do this denoising process, some libraries actually don't have this function implemented, right? So what we do, something very simple, is we add this clipping function, right, just to make sure the latents, right, those intermediate images, denoise images, right, will remain in the right pixel value range. And with this simple idea, right, at least on DDPM, right, we found it to be very effective, right? So these dashed lines are the inference time clipping, right, with this clipping enabled, and then these solid lines are the inference without clipping, right? So we and then I'm showing you the mean square error, right? So a lower mean square error means the attack is more successful. So what we can see is that you, by simply implementing this inference time clipping, right, you can remove the backdoor. And my hypothesis is that the backdoor is actually learning the associations through these latents, right? So if you limit the expressibility of those latent images, right, you're actually limiting the backdoor to generate a target image from a trigger pattern. So that is our hypothesis, and maybe like what was discussed, right? Maybe some disentangled analysis, right, can help us understand why clipping, right, during inference, right, changes the output of the model significantly. So finally, I would like to quickly show you something that is that we are working on right now, and actually some work that we submitted for reviews. I don't want to talk too much about it, but this is just the idea of what I showed you before is the triggers in the image space, right? What we can actually do is we can actually assign triggers in the text domain too, right? Like this is exactly how Stable Diffusion is doing, right? So you provide a text prompt, and then the Stable Diffusion will generate an image based on the prompt you described. Right, so this is an example of we can extend this idea to also backdoor text-to-image diffusion models, right? So the prompt that we are trying here is like she has no eyeglasses, no fringe, and a big smile with her mouth a little open and teeth visible. The person looks extremely young. So what we did is we can now insert a trigger pattern right here. The trigger can be a word like a Migneko or a word like anonymous, right? And then we assign these triggers to different target images. So what we will see is that for clean generation, which means without adding the additional trigger at the prompt, right? You can still generate images very good, right? Following the description of the text prompt. But with the trigger added to the text prompt, right, it will generate those target images, and those cat images or those this anonymous hacker image, right? So this is showing that our idea, right, can be extended to these text-to-image diffusion models as well. Okay, so any questions or comments? Okay, so I just want to provide a summary of what I show you today, right? So we are basically introducing a technique called the bad diffusion, right? So the high-level idea is to add a correction term to the mathematical diffusion process, right, to control the denoising steps of the diffusion models as a way to efficiently inject backdoors to the diffusion model. And we have shown that this backdoor attack can be done in a very low-cost way, right? We only need to take a pre-trained model as a starting point. And then the attacker can have an ability to achieve a high specificity and high utility backdoor attack on different types of diffusion models and different data sets. We also show some simple but somehow promising defense or inference time clipping to remove or to mitigate the backdoor effect of diffusion models. And I don't have time to go into those other topics here, but I think we have a good discussion on that, like a concept evasion, like watermarking, IP protection, that kind of thing. So yeah, so feel free to reach out to me if you have any question in this domain. And then we have the papers online and also codes available. So feel free to reach out to me if you have any question or any interest in exploring this idea further. Thank you.
Yeah, thank you so much, Dr. Pinho. This was a very insightful session, and I'm sure everyone here, as well as those who will watch the recording online, will learn a lot from it. And if anyone has any questions, please do reach out to Dr. Pinho on the email. I will add that to our channel as well, to if anyone wants to reach out to them. And from personal experience, like I've had the pleasure to work with Dr. Pinho as well on research projects before, and they are one of the most understanding and like helpful collaborators you can find. So if you do have any research ideas regarding adversarial robustness or anything related to the robustness domain, I would encourage you to reach out to Dr. Pinho as well.
Thank you, Neil, for the nice words.